Hello students, myself Geeta Mishra, and today's my lecture topic is heterocyclic compound, uh, pyridine. So these are the heterocyclic compound, and it is a six-member heterocyclic compound which contains the nitrogen as a heteroatoms. So here six elements are present in cyclic structure of pyridine, which contains one nitrogen heteroatoms with one non-bonded electron, and this nitrogen is assigned lowest number over here and move towards from this or this direction. So if we see the planar structure about the pyridine, so look at here, each of the carbon have the pi orbital, and one pi orbitals are pi orbitals which contains one pi electrons are present over here, and nitrogen which is sp2 hybridized orbitals like this carbon and this carbons. So these are all the pi electrons or pi orbitals. These are located parallelly to each other. That's why they are able to uh, delocalize the pi electron with each other. And one more pi. So look at this nitrogen, and it contains the sp2 hybridized orbitals that contains the lone pair of electrons, and these are non-bonded electrons. So pyridine have the 5 carbon and 1 nitrogen, and all are the sp2 hybridized. So sp2 due to the sp2 hybridization in all of the compound 5 carbon and 1 nitrogen, the if we see the structure of the pyridine, it is a planar structure which contains the planar ring structure, and each ring atoms also contains the unhybridized p orbital that is perpendicular to the plane of the sigma bond. That's why the p orbitals are uh, parallel to each other, and they are ready to overlapping between the p orbitals electrons. So the total number of the non-bonding electrons are 6, 5 of the carbon and 1 from the nitrogen. And these 5 and 1 nitrogens are overlap with each other, each of the p orbitals, and make a pi molecular orbitals. So by the formation of pi molecular orbitals, they follow the Huckel rule. That's why they have the specific characteristic like aromatic characteristic in this compounds. So the pyridine is produces the aromaticity. Now next property of the pyridine is basicity. So due to the presence of the nitrogen, it is act like a base, but pyridine is the more basic than the pyrrole. So if here we are talking about the pyridine basicity. So as we have discussed in previous heterocyclic compound discussion, the pyrrole is also contains the nitrogen as a heteroatom in the 5-member heterocyclic rings, and pyrrole is also a basic in nature. That's why we have the reason here to compare the basicity of the pyridine and pyrrole. Which one is more basic in nature? So pyridine is more basic than the pyrrole. What is the reason behind this? Why the pyridine is more basic than the pyrrole? So pyrrole, here look the structure. It is a 5-membered ring which contains the nitrogen, and it has a 1 non-bonded electrons, and here it is a 6-membered ring which contains the nitrogen, and it is sp2 hybridized orbitals is also here, which contains the lone pair of electron. So uh, basicity is depend upon the availability of lone pair of electron. If we see the structure of pyrrole and the structure of pyridine, so we can see here the pyrrole, which contains the lone pair of non-bonded electrons, these are involved in the resonance process. This delocalization of pi electrons are possible in the this structure, and these lone pair of electrons which are present over the nitrogen is involved in this resonance, in this formation of pi molecular orbital. But here in the pyridine structure, look at here, this nitrogen have already one electrons, and 5 carbon pi electrons are involved in the pi molecular orbital formation delocalization process, but one non-bonded lone pair of electrons are free for the acid-base type of reaction. So that's why, because the nitrogen contains one extra non-bonded electrons which are free from the delocalization of pi electrons, that's why they are not participating in the resonance process. Here in pyrrole, this lone pair of electrons are involved in the resonance process. So by this reason, this pyridine which contains the lone pair of electrons are involved in the acid-base reactions, or any further reaction, they are free to here for ready for the and available for the reaction with another molecule. That's why the pyridine is more basic than the pyrrole. So here the reason is given to here, the electron in the same pyridine hybridized orbital plane, so it is not participating to the resonance phenomena. That's why the lone pair of readily available for the acid-base reaction. In pyrrole, the electrons perpendicular to the plane of pyridine hybridized orbital, it participates in the resonance or delocalization of pi electrons, and they are not readily available for the acid-base reaction. Due to this reason, pyridine is more basic than the pyrrole. Next, the basicity of pyridine is less than the aliphatic amine. In previous slide, we have discussed about the basicity of the pyrrole and pyridine. Over there, the pyridine is more basic than the pyrrole. But in this condition, the aliphatic amines is more basic than the pyridine. Reason? What is the reason over here? So pyridine nitrogen contains the pi electrons which are sp2 sp2 type of hybrid electrons, and it contains the more s characters. sp2 hybrid orbitals which contains the lone pair of electron. That's why it is very more electronegative in nature, and they have the more s characters. And here in aliphatic amines, here see the lone pair of electron, and this nitrogen is looking like a sp3 hybridized. Due to the sp3 hybridization of this nitrogen, it is less electronegative. And here the due to the less electronegative, the electrons are more closely held together and more electronegative nitrogen. So that's why here no nitrogen or electronegative nitrogen are available for the acid-base reaction. As a lone pair of electron is not readily available in pyridine, it is less basic than the aliphatic amine. So repeating this, the basicity of the pyridine is less than the aliphatic amines. The reason is sp2 hybridized nitrogen is more electronegative. Okay, so if we compare about this nitrogen and this nitrogen, one pyridine nitrogen is sp2 hybridized nitrogen, and aliphatic amine is sp3 hybridized in nature. So here it is this nitrogen is more electronegative and this is less electronegative. So reason is this: the sp2 hybridized nitrogen is more electronegative than the sp3 hybridized nitrogen. So lone pair of electrons of lone pair of electron are more closely held towards the more electronegative nitrogen. So this nitrogen nucleus is bonded to this lone pair of electron is very tightly, or very closely they are bonded with each other, or there are the attraction forces between the nuclei of the nitrogen. That's why there is these lone pair of electron are less available for the acid base reactions. That's why this pyridine is less basic than the aliphatic amine. So aliphatic amine, which contains the lone pair of electron, this lone pair of electrons are less electronegative because their lone pair of electrons are not closely held with the nucleus of the nitrogen. That's why they are freely available to react with acid base reaction. That's why aliphatic amine is very basic than the pyridine. Next property is tautomerism. So for the tautomerism of pyridine, here one conditions are required. If the pyridine is substituted at second or fourth position with the group like oxygen or nitrogen or sulfur, then it may possible the form of tautomerism. Look at here one oxygen is present over here. So they have ready to get the protonation process. So 2-hydroxypyridine, which is present in the 2 form, 2-hydroxypyridine and 2-pyridone. So this hydrogen is as a hydrogen bond acceptor, or this pink color nitrogens are looking like a hydrogen bond donor. So this hydrogen is maybe switched over here by the delocalization or obstruction by the obstruction of proton from the here, and they may produce a 2 type of structure like a 2-hydroxypyridine and 2-pyridone. Next property is hydrogen bonding. Hydrogen bonding, pyridine is a water soluble because their non-bonded electrons or sp2 hybridized pi electrons are involved in the hydrogen bonding. Due to the formation of hydrogen bonding by the water molecule, they are easily soluble with water. So here the synthesis of the pyridine, here some of the synthesis are given here, which are used for the synthesis of pyridine. The first reaction by which we can synthesize the pyridine is Hans pyridine synthesis. In this reaction, the condensation of aldehyde with 2 mole of beta dicarbonyl compounds and ammonia. So here 1 aldehyde and 2 mole of beta dicarbonyl and ammonia. Here 3 molecules are required, 2 beta dicarbonyl compounds and 1 ammonia and aldehyde. So in these three or four molecules are condensed with each other and form the dihydropyridine. So over here, this nitrogen is bonded with this, form the bond with this carbon, and over here, this oxygen is moved to here and form the bond from here, and here one bond will be formed between this carbon and this carbon, and this nitrogen and this carbon is bonded with each other by the condensation process and form the dihydropyridine. By the oxidation in the presence of nitric acid and sulfuric acid, it form the aromatic pyridine ring. Okay. So by the formation of aromatic pyridine ring in the basic media on and uh, alcoholic KOH, and it whenever this will be heat, there is the decarboxylation process uh, will be undergo, and the 2-dimethyl pyridine will be formed. So by this Hansch pyridine synthesis, condensation of aldehyde and beta dicarbonyl compound and ammonia. Next synthesis for the pyridine is the Borashi synthesis. By the this is the modified Hansch synthesis by use of the cyanoacetamide as the nitrogen containing component. In the previous Hansch synthesis, we have used for the nitrogen atom, we have used the ammonia, but here we are using the cyanoacetamide for the nitrogen element. So by the condensation of these two dicarbonyl molecules and with the cyanoacetamide in the presence of K2CO3 and acetone, it form the pyridone. By the condensation process, this nitrogen and carbon bond will be formed over here. This carbon and this carbon will be joined together here and form the 2-pyridone. Another example, 3-alkoxyenones with any nitriles, we can form the 2-pyridone. Another synthesis is from the 1,5-dicarbonyl compounds. So when ammonia react with 1,5-dicarbonyl compounds, it gives 1,4-dihydropyridines, which are easily dehydrogenated to pyridines. So look at here, it is a 1,5. If we naming over here 1, 2, 3, 4, 5. 1,5-dicarbonyl, two ketones groups are over here. 1,5-dicarbonyl compounds, whenever react with ammonia, it will condense with each other and form the cyclic ring. So by the removal of the 2 mole of water, here 1,4-dihydropyridine will be obtained. On the oxidation in the presence of nitric acid, it will be further converted into the substituted pyridine. So after the synthesis of the pyridine, we are moving over the reactions of the pyridines. So which type of reactions are undergoes in the pyridine? So first reaction is electrophilic addition to nitrogen. So in this electrophilic addition to the nitrogen, there are two reactions. One is protonation and second is N-alkylation, which is similar as pyrrole molecule, pyrrole and pyrazole molecules, which we have discussed in earlier. So here the pyridine is reacted with HCl. Nitrogen will get protonated and form the pyridinium chloride salt. And this molecule is react like a basic in nature. And alkylation, whenever any alkyl halide are reacted with pyridine, it form the alkyl pyridinium iodide. So 1-methyl pyridinium iodide is formed with nitrogen. Next reaction, imidazole is approximately 100 times more basic than the pyridine. So imidazole, which we have discussed in previous session. So if we compare the basicity of the imidazole and pyridine, so imidazole is more basic than the pyridine. The reason behind this is the protonation of imidazole yields an ions that is stabilized by the electron delocalization. So if we protonated the pyridine, we can get only one structure, pyridinium chloride. But in case of imidazole, whenever it get protonated, there is the two resonance uh, electrons delocalized uh, cations are available here. So here one nitrogen get cationized, and here another nitrogen get cationized. So form the imidazolium cations, and these imidazolium cations are having the two cationic structure, two resonated cationic structure, which are more stabilized than the pyridinium chloride. That's why the imidazole is more basic in nature than the pyridine. Now, another reactions of pyridine is electrophilic substitution to carbon. So, mainly pyridines are more preferable for the electrophilic substitution at third position. So if we see the electrophilic substitution reactions at the different positions of the pyridine, so at the C2 position, C3 position, and C4 position, but the C3 position are more susceptible or more preferable for the electrophilic substitution compared to the C2 and C4. The reason behind this is nitrogen is electronegative, so the positive charge on the nitrogen destabilizes the structure. So if we see the electrophilic substitution on the C2 and C4 compound, look at here, the formation of N positive intermediates, N cationized intermediates are formed over here. That's why they are less stable or less favorable than the nitrogen nitrogen positive intermediates. And in C3 electrophilic substitution, here no intermediate is formed as the which have the nitrogen positive charges. Look at here, any of the resonated structure does not contain any type of positive charges over the nitrogen. And if we see the C2 here, look at here, this nitrogen contains the positive charge, and these are the resonating structure of pyridine at the C2 position. At C4 position, if C4 position are ready to for the electrophilic substitution, look at here, one intermediate are also present in this resonating structure which contains the positive charge, and these positive charge which get by the nitrogen, these are the destabilized structures for the electrophilic substitution. So by this reason, the only C3 positions are more preferable for the or more favorable for the electrophilic substitutions. So here examples of the electrophilic substitutions are nitration and sulfonation. So nitration in the presence of sulfuric acid and nitric acid, the third position is get substituted with nitro 2. And for sulfonation, generally pyridine is very resistant for the sulfonation process, but one specific conditions in which the sulfonation process will be very smoothly happened. So look at here, if the mercuric sulfate are also taken in the reaction media as a catalyst, as a catalytic quantity with the sulfuric acid, we can get the sulfonated pyridine. So here at third position, the sulfonation will be happening. And halogenation, by the pyrimidine in the presence of different condition for bromination and chlorination. Here aluminum chlorides are responsible for the chlorination, and for bromination oleums are required for the bromination process. So 3-bromo-pyridine is produced in good yield by the action of bromine in oleum. And 3-chloropyridine is in the presence of aluminum chloride. Now, another reaction which is possible in the pyridine molecule is nucleophilic substitution. These molecules are very important, which contains the both type of substitution reactions, electrophilic substitution reactions and nucleophilic substitution reaction. So remember this point for for the pyrimidine molecules. There is the important point which is required to remember for every students, that is the this pyridine molecules which contains the both type of substitution reactions, like electrophilic substitution reaction as we have discussed in previous slides, and the nucleophilic substitution which we are discussing over here. So why the pyridine undergoes the nucleophilic substitution reaction at second position? As we have discussed, the electrophilic substitutions are possible at the C3, C4 and C5, C2, C3 and C4, but for the nucleophilic substitution, only second position are susceptible for the nucleophilic substitution. So any nucleophile when substituted over say C3 or C2, then C2 positions will be more preferable for the nucleophilic substitution. So if nucleophile get attacked at C3 position, look at here, the negative charge will be moved and form the resonance intermediate structures and will get substituted by the nucleophile agents. And here at second position, when so second position is attacked by over here, so here the possibility of the resonance structures over here, and especially in the C2 position nucleophile attack, we get the one intermediate structure at which the nitrogen having the negative charge, which is more stable for the nucleophilic substitutions. So attack on the second position gives the more stable intermediate containing negative charge on the nitrogen. That's why the nucleophilic substitutions are more stable in the C2 position. As we have discussed in the electrophilic substitutions over there, the C3 position are more susceptible for the electrophilic substitutions, because their C2 and C4 resonance stabilized structure contains the nitrogen positive charge, which destabilizes the structure of pyridine. But over here, the nitrogen which contains the negative charge, that is stable, more stable form of the intermediate structure or resonance hybrid structure. That's why C2 position is more susceptible for the nucleophilic substitutions. So here the examples of the nucleophilic substitutions over here. If pyridine is reacted with sodium hydride or sodamide in the presence of ammonia at the high temperature, it forms the pyridine to amine. Amine will be substituted over the second position. So this nucleophile attack at the second position. When this NH2 group is attached with this, then this nitrogen, this pi bond will move over here and form the bond here, and this bond will be shifted to here, and this bond will be shifted to here, and nitrogen get contain the negative charge over here. So this is the structure will be formed in the second step. By the elimination of the one proton, one hydrogen will be eliminated from here, and the bond will be formed between this and form the pyridine to Me. Next reaction is pyridine as a nucleophilic catalyst. So sometimes various synthetic process or various type of synthesis for the medicines or various drugs are synthesized in the presence of pyridine as a catalyst. So these are also act as a nucleophilic catalyst. So this is a very important molecules or very important compounds which are essential in the various type of synthetic reactions for the formation of drugs. So it is used as a catalyst for acylating phenols, alcohol and amines using the acyl chloride or anhydrides. So if we see here one example for the alcohol with acyl chloride. In the presence of pyridine, it form the esters. So various drugs which are formation of the prodrug or there is for their esterification process. These are the pyridine molecules is used as a catalyst, and by the nucleophilic catalyst, it first attack on the acyl chloride at this electron deficient nitrogen. Whenever this will be attacked over here, this chlorine will be get released from the here. This bond will be break and the chlorine will be released or leave from here, and this pyridine molecules get attached with the acyl group. Whenever this attached with the acyl group, this carbon will be electron deficient, and the alcohol which contains the hydroxyl group, and these hydroxyl groups will attached over this electron deficient group and form a bond between the carbon and oxygen. So look at here, carbon and oxygen, and this R group are here. And after that, whenever this bond will be formed over here, then this pi bond will be break and oxygen contains the negative charge. Whenever again this negative charge will form the double bond over here, then this carbon will be unbalanced, and over here this nitrogen and carbon bond will be break and pyridine is released, because it was used for a catalytic purpose only for the catalysis process. And after the initiation of the process and formation of molecules, these pyridine molecules will be released from the here and form the ester molecule. So it is also used as a nucleophilic catalyst in various reactions. So for reactions is also possible in the pyridine molecules in the presence of catalytic reduction, or in the methanol and sodium presence of any metals, it will be reduced in the pyridine. So after the discussion of the properties of the pyridine and their synthesis and reactions, chemical reactions related to pyridine, the most important portion of the pyridine is the medicinal uses, where these are used as a hybrid structure in the as a drug molecules, which are used in the various type of treatment of the diseases. So antitubercular agent isoniazid, which contains the nitrogen containing these pyridine molecules, which is essential for the tubercular activity. And antibacterial agent like sulfapyridine, sulfasalazine, it also contains the pyridine ring, which are essential for the hydrophilicity of the, for improvement of the hydrophilicity of the, or binding to the receptor for the antibacterial action. An anticholinesterase agent for the pyridostigmine. It is used in the Misthania gravis. It also contains the pyridine molecules. And the most important in the proton pump inhibitor, like drugs are omeprazole, lansoprazole, pantoprazole, rabeprazole. These pyridine containing drug which are used in the peptic ulcer here, because they are controlling the proton pump inhibitor. They are act as a proton pump inhibitor and used in the treatment of peptic ulcer. Omeprazole, lansoprazole, pantoprazole, and rabeprazole. So another use for the pyridine is the as a vitamin. So these are helps in the digestion and digestive system health, and also help in the processing of the carbohydrate. And these pyridoxal phosphate, which are used as a brain chemical and needed for the brain system, and very helpful in the immune system of the cells and RBC cells.